A bit flip error is exactly what it sounds like. A bit that should be 0 becomes a 1. A bit that should be 1 becomes a 0. Silently, randomly, without warning. In classical computing, this is a familiar nuisance. In quantum computing, it's a much more serious threat, because a flipped qubit doesn't just carry the wrong value. It can derail an entire computation before anyone detects that anything went wrong. Classical engineers solved bit flip errors long ago. The trick is redundancy. Instead of sending one bit, send 3 copies of it. If the original is 0, send 0, 0, 0. If a single bit flips during transmission, one of the 3 will be wrong. A simple majority vote catches it. 2 zeros and 1 wrong one still votes for 0. The error is detected and corrected without ever knowing exactly when the flip occurred. Here's how the majority vote works. 3 copies travel through a noisy channel. At the other end, all 3 are compared. If all agree, the result is trusted. If one disagrees, the 2 matching ones outvote it, and the error is corrected. A single flip anywhere in the 3 copies is caught automatically. 2 simultaneous flips would fool the code. But at low noise rates, that scenario is far less likely than a single error. Now try to use the same trick on a qubit. You want to copy the qubit 3 times and send all 3 down the channel. But there's a problem this series covered earlier. Quantum states cannot be copied. The no-cloning theorem makes it physically impossible to duplicate an unknown qubit state. So the classical fix, simple and elegant as it is, cannot be directly applied to quantum information. A different approach is needed. In quantum computing, a bit flip error is formally the X gate applied accidentally by the environment. A definite 0 flips to 1, a definite 1 flips to 0. And if the qubit was in superposition, the flip swaps its 2 amplitudes, exchanging the weight on 0 and the weight on 1. The superposition survives, but it now carries the wrong information. And nothing about the qubit's outward appearance signals that the swap occurred. The quantum fix uses entanglement rather than cloning. 2 controlled NOT gates spread the logical qubit across 3 physical qubits in a specific entangled state. Logical 0 becomes 3 physical zeros. Logical 1 becomes 3 physical 1s. This isn't copying the state. The 3 qubits together hold 1 logical qubit through entanglement. A flip on any single physical qubit disturbs this shared state in a way that can be detected without reading the data. To find the error without reading the data, 2 parity checks are performed. The first checks whether qubit 1 and qubit 2 agree.
The second checks whether qubit 2 and qubit 3 agree. These checks don't reveal the actual bit value, only whether a disagreement exists and where.
The 2 results form a syndrome that pinpoints exactly which physical qubit was flipped, without disturbing the logical qubit's superposition at all. Once the syndrome identifies the flipped qubit, a corrective X gate is applied to exactly that qubit, flipping it back to its correct state. The logical qubit returns to its original encoded form. This entire cycle, encoding, noise, syndrome measurement, and correction, never directly reads the logical information. The superposition is preserved throughout. The logical qubit survives the flip reliably, and the process can repeat as many times as needed. But this code only handles bit flip errors. Phase flip errors, the Z-type errors, pass right through it undetected. And the real environment produces both simultaneously. Protecting against bit flips alone is only half the job. The full solution requires a code that catches both error types together, which is exactly where quantum error correction goes next, and why the field needs codes far more sophisticated than this one.